In the previous two modules, we have focused on developing powerful meanings for graphs, tables, and formulas to represent how the values of two quantities change together. This is such an important idea that we will review it here before learning some new ideas and notation to talk about these relationships. So let's recall the following context. Let's imagine unwinding rope from a spool. The rope weighs 0.8 ounces per foot. And we'll imagine placing a 4-ounce hook at the end of the rope. So I have this shown here. So we can vary the amount of rope that is unwound from the spool. We have a 4-ounce hook at the end of the rope. So we will let X represent the number of feet of rope unwound. We'll let W represent the weight of the rope and hook in ounces. So as we unwind rope from the spool, both X and W increase. Now let's fill in a table of values showing a few pairs of X and W. So when X is equal to 3, which means that 3 feet of rope have been unwound, then the corresponding weight of rope and hook is 0.8 times 3, which represents the weight of the rope in ounces. And then we'll add 4 ounces for the weight of the hook. And this is equal to 6.4, which means that when 3 feet of rope have been unwound, the weight of the rope and hook is 6.4 ounces. Similarly, if X is equal to 7, then the weight of the rope is 0.8 times 7 ounces. And we'll add 4 ounces for the weight of the hook. And this is equal to 9.6, which means that when 7 feet of rope have been unwound, the weight of the rope and hook is 9.6 ounces. Now in general, if X feet of rope have been unwound, then 0.8 times X represents the weight of that amount of rope. And if we add 4 ounces for the weight of the hook, then this expression right here represents the weight of the rope and hook together. Now when we have generalized the value of one quantity in terms of another in this way, we have the understanding that this lets us write a formula. Since W represents the weight of the rope and hook in ounces, we can write the formula W is equal to 0.8 times X plus 4, which expresses the weight of the rope and hook in terms of the number of feet of rope unwound. Now, this formula, let me move this down a little bit. This formula allows us to actually add entries to our table of values. So for example, if 10 feet of rope have been unwound from the spool, then we can use our formula. We can evaluate our formula at X equals 10, which results in 0.8 times 10 plus 4, which is equal to 12. And this means that when 10 feet of rope have been unwound, the weight of the rope and hook is 12 ounces. Now, we can also graph the relationship between W and X. So notice that I have a few points plotted on this graph, and these represent some of the pairs from the table of values. So we can plot our pairs from our table of values on the graph, and these points are always going to lie on the graph. However, there are also a lot more points on the graph than there are on the table of values. And this is because the graph, similar to the formula, represents all possible pairs of X and W. So there are infinitely many points on this graph, and each point on the graph represents an XW pair, which tells us a pair of values for the length of rope unwound and the weight of the rope and hook. Notice also that we can use the graph to determine new points for our table of values. We can use our table of values to plot points on the graph. We can use our formula to plot points on the graph. And we can use the graph to actually determine pairs that satisfy the formula. So in a large way, all three of these representations are deeply related. Now, these three representations all represent the way that the values of the two quantities must change together given the constraints in the problem. Understanding how to interpret the representations, use them, and move back and forth between them is key to developing powerful understandings for the relationships that we are modeling.